Okay, perfect. All right, welcome everybody to another MCRN Colloquium. Today we're joined by Dr. Blake Barker from Brigham Young University. Blake earned his PhD with Kevin Zumbrun in 2014 at Indiana University. He was an NSF postdoctoral fellow at Brown after that. And then since then, he's been in the applied mathematics department at BYU. His research interests are stability of traveling waves in a variety of physically motivated systems. Also magnetohydrodynamics, shallow water equations, and his research lies at the intersection of numerical analysis, PDEs, and dynamical systems. Today, he'll talk about rate-induced tipping in a moving habitat. Very much looking forward to it. And with that, Blake, yeah, please.
All right. Thank you very much. I appreciate it. So if you look on the internet, you can find several examples of habitats that are moving. So for example, this picture here is taken of the coral reef. The coral reefs are moving away from the warmer equator. We've got the interface between ice and land. That's a moving habitat. The boreal forest is another example. So today I'm talking about a moving habitat problem, which incorporates the distribution of a species on that habitat and how that species adapts to the habitat as it moves. This is work in collaboration with Emmanuel Thornton, Matt Holzer, Chris Jones, and Sebastian Wisorek. And with that, there we go. Okay, so the highlights of the talk are the following. We're going to talk about this moving habitat, and we're going to characterize what causes tipping. That is, what makes the difference between the species adapting to the moving habitat opposed to going extinct when the habitat moves. And this characterization of tipping is going to involve a heteroclinic solution between two stationary solutions of a partial differential equation. So the analog of a heteroclinic connection that we would have in ODE theory. This work deals with rate-induced tipping and PDEs, and of course it has the application to ecology. So in these pictures, we're seeing the boreal forest, or the taiga is another name for it, here in Alaska on the right. And then here on the left, it's on the north shore of Lake Superior in Minnesota, which is sort of the southern boundary of this forest. And it's one of the things that are moving. So as we're going throughout the talk today and thinking about a habitat moving, I would think about the boreal forest. So over a long time scale, the forest itself is moving further north. So what is tipping? For our purposes today, we'll consider tipping to be a change in the system behavior that corresponds to a sudden transition from a stable state to some other state. It could be a different stable state, or it could be a transient state. And it's disproportionately difficult to reverse from the state it goes to the state it comes from. So the classical example, of course, is we have a ball rolling down a hill, we have these local minima, and it's much easier to push the ball from the left to the right than it is from the right to the left. So today we're talking about rate-induced tipping, but some other types of tipping of interest are bifurcation-induced tipping, whereby noise in the system causes some realizations of the solution to reach a point where it's difficult to reverse the state of the system. There's also, or sorry, that was noise-induced tipping. There's also bifurcation-induced tipping where a parameter changes. Think of like a pitchfork bifurcation. And then rate-induced tipping, whereby there's a ramp parameter. And as that ramp parameter changes, if it changes too quickly, the system can undergo changes that are hard to reverse. And what sort of happens is the ramp causes the basin of attraction to move, and the state just sort of can't keep up. It can't track the underlying state, the underlying steady state. And so you get the long-term behavior going to some other solution. The model we'll be talking about today is this reaction-diffusion equation. given by this PDE. The species population is represented by U, and this accounts for both diffusion of the species and then a reaction term to account for the interaction between the species and its habitat. Gamma is a function corresponding to the shift of the habitat or the movement of the habitat and is time dependent, posed on the whole real line. T is on the whole real line. The reaction term, as we'll see here in a little bit, gives us an interaction of a nonlinear interaction of the species with the habitat as well. The habitat function corresponds to the location where the habitat is, and that it looks like a pulse. I'll show you in a moment. And it moves as well with time because of the dependence on x minus gamma. And then our rate parameter is r, and the shift is given by a tang of rt. So we will see that for r sufficiently large, the species will go to extinction. For r sufficiently small, the species will undergo adaptation to the habitat shift. And then there's a critical R that we characterize that divides between these two regions. This picture here on the left is a characterization of the tipping, which we'll talk about in more detail. What we have on the upper left of this figure is a pulse that corresponds to a steady state of the time asymptotic system of this PDE. So it corresponds to a stationary solution of that asymptotic system. And that is a state where the species is in perfect balance with the available habitat and the population of the species. And then red corresponds to another stationary solution of that same system, but it is an unstable state. And so any small perturbation of that state results in the species moving, and it turns out moving to the stable state or to extinction. And the characterization of the tipping point is a heteroclinic connection between the stable pulse and the unstable, stable shown in blue, unstable shown in red. So that is where we're going with this talk. The habitat function that we've already mentioned looks like this smoothed hat function, or smoothed, this piecewise smoothed function. And it corresponds to the location in this picture of green. So this corresponds to the boreal or taiga forest. And so we should think of the habitat function being 0 outside the region where the forest is, being 1 or close to 1 for the majority of it. And then there's a small transition region between the existence and non-existence of the habitat. And then the shift goes from negative a to a in this figure on the left. A is equal to 2. So this is a shift of a total distance of 4, which we'll call d. And this shift happens more rapidly near time t equals 0, and then very, very slowly asymptotically as t goes to plus and minus infinity. R again is the ramp parameter that corresponds to how quickly the transition region occurs. The reaction term F, which is a function of the species population in the habitat function, here is given as follows. Now, when H equals 0, when we're outside the habitat region, for positive or at least non-negative populations, we get that F is negative, so the overall effect is to bring the population down, as it should do, because there's not habitat to support the population. And then on the right, that corresponds to H equals 1. For U positive, that corresponds to growth. So the species can grow because it has not reached its carrying capacity for the habitat available. So that gives an idea of how the reaction term affects the species growth. And one other aspect of this is the diffusion part. So I've watched, a few of these nature videos, and as I understand from those, mountain lions, for example, are territorial. They will fight each other for the territory. They need a large area. And so if there's a high density of these mountain lions, then they'll spread out to other regions to try and find territory where they can claim it and have their own place to hunt. So of course we have the opportunity for the species to diffuse and move from areas of underutilized habitat, from overutilized habitat to underutilized habitat. All right. So let's talk about the time asymptotic system. So if we take our PDE and we take the limit that t goes to plus or minus infinity, we're left with this system, this reaction diffusion system here, which has two stationary solutions that we've depicted here with black and blue on the right. The black one is a stable steady state, and the blue one is an unsteady state. So small perturbations of it will either go to zero or to the stable steady state. And if we take, for example, just a little, if we take just something like a pulse and add to it, you can see numerically that things go up, and if you take the negative of that, they go down. So these are what we refer to as the stable and unstable pulses, and they correspond to the steady states of the system before habitat transition has occurred. And then again after. So here we show numerically a solution to the original partial differential equation. We have done a coordinate change so that the center, so that it kind of centers the population as the habitat moves about the center of the habitat. So in this figure, what you see is originally at the top left of this bottom left figure, you see the original population, and then the habitat moves. And so it's like the species is moving instead of the habitat under our coordinate change. So the species moves, but then comes back to center around the habitat. So this would correspond to the ramp parameter r being small enough that the species is able to adapt. And then on the right, the ramp parameter is large enough that the species is not able to adapt to the moving habitat. It's not able to align itself back with the habitat, and it ends up going to extinction. We've plotted this with a log scale in order to show the dynamics better. And in between these two cases that we just saw, there is a heteroclinic connection, a connection between the stable pulse and the unstable pulse as t goes to minus infinity and to plus infinity, respectively. And this, it turns out, characterizes the tipping point. What we'll do is show evidence that this characterizes the tipping point. We'll look at linearizing this heteroclinic connection, linearizing the PD about this heteroclinic connection, and taking the inner product that shows that if you have the solution and you change the R parameter a little bit, that you'll go to extinction in the downward direction, or in the opposite direction, you'd go to adaptation. All right, so that's the main result. Now, it turns out that in order to have R tipping, you do need to have the shift of the habitat sufficiently large, which makes sense physically. If there's just a really small shift in the habitat, then we would expect the species to be able to adapt. In fact, there's always little shifts in the habitat. So we have some critical distance of habitat transition, D star, that corresponds to anything less than that if A is small enough, the A for the gamma function is small enough, that is if the distance of the shift is small enough, then there's no tipping. And if it's large enough, then there is tipping for R sufficiently large. R should be on the y-axis. It looks like that picture got, but the axis got excluded here when I moved it. So R tipping does occur for a sufficiently large rate parameter R. And then on the right, we can kind of show you the interplay where that critical R occurs for different values of L and D. Okay, so as I mentioned, we make a change of coordinates for the partial differential equation in order to think of the habitat as being centered, and it's sort of the species that's moving, and about that center. Now, when we make this coordinate change, we introduce a term gamma sub t, and gamma sub t approaches zero asymptotically as t goes to plus and minus infinity. And for this system, when gamma sub t goes to zero, we're left with that time asymptotic system that we wanted to solve in order to get the stable and unstable pulse. So let's talk for a few minutes about how we solve for those pulses. So we discretize the system in the following way. We assume that the solution is a finite sum of Chebyshev polynomials. So d sub z tilde corresponds to changing the coordinates so that our truncated spatial domain z lies between -1 and 1, the basis for the Chebyshev polynomials. And then this corresponds to the second derivative operator on that space of Chebyshev polynomials. And then f is evaluated at the Chebyshev nodes. So what we're doing is a spectral method for solving for the solution. And it turns out that using a pulse, just like a sesh, as an initial guess for a nonlinear solver for the coefficients of that Chebyshev sum is sufficient to find the blue unstable pulse. And then H is a good guess to find the stable pulse. This d z tilde operator is designed for having Dirichlet boundary conditions, so having u equals 0 on the boundaries. So solving this finite dimensional ODE system gives an approximate solution to the partial differential equation. It's useful to think of the original PDE in compactified form, so as a compactified system. And to do that, what we do is introduce the variable gamma. Gamma is the habitat transition function. And we know that it's equal to A tang of RT. And so we can recover the differential equation it satisfies. So we write this as a compactified system, which removes the explicit dependence on time, so that we then have a system that is more convenient to work with and has some nice properties for thinking about the problem. Now let's talk for a bit about how we numerically solve for these solutions. So again, we'll use a Chebyshev basis. So this is a pseudospectral method where, similar to how we did before, we consider V to have a solution that consists of a finite sum of Chebyshev polynomials. Our goal is to solve for the coefficients of that system. V is evaluated at the Chebyshev nodes, and then dz tilde and dz tilde correspond to the derivative operators acting on that Chebyshev polynomial. So we solved this in MATLAB, both as an initial value problem and as a boundary value problem. When solving it as an initial value problem, we initialize for a value that corresponds to the t being very negative, so that we capture the asymptotic behavior, and then we solve forward sufficiently long to see the behavior. And when we'll talk more in a minute about solving it as a boundary value problem. So here on the left, this is the solution to our Chebyshev ODE system that we've mentioned here, both in the case of there being adaptation, there being extinction on the right, and then there being a heteroclinic connection characterizing tipping. To solve this system as a boundary value problem, we would want to have projections onto the stable subspace at t equals -infinity be 0. And we'd want projections of the solution to this ODE system onto the unstable subspace to be 0 at t equals +infinity. The fixed point of this ODE system corresponds to the stable and unstable poles. The fixed points correspond to these. And so we look at the stable and unstable manifolds of those fixed points and make projections accordingly so that we get a solution that leaves along the unstable manifold and comes in at t equals +infinity along the stable manifold. The reason why we consider these two methods is the following. Considering it as an initial value problem makes it straightforward to compute. Solving it as a boundary value problem gives us more accuracy and allows us to impose boundary conditions so that this becomes an approximation of the PDE solution on the entire line. Now, one of our goals, as we mentioned, is to show that this heteroclinic connection between the stable and unstable poles characterize tipping. By using an initial value solver, we see that for r bigger than some critical r, which we can refer to as r star, that the solution goes to extinction, it goes to 0. And for r less than that, it goes to the stable poles, it goes to adaptation. So we see that there is, you can already see that there appears to be this relationship between the solution and how it relates to this unstable poles. So what we're going to do is solve for the heteroclinic connection, and we will refer to that solution with hats. And then we're going to linearize the partial differential equation about that solution. And when we linearize it about that solution, we'll then take the inner product of the solution to the linearized problem at +infinity with the unstable eigenvector of the ODE system that we solve numerically, which corresponds to the unstable manifold of the unstable poles. So we'll take that inner product and we'll show it's negative. So that indicates that right at that R critical, small perturbations of the system that are, small perturbations of the system will go to extinction if you're below you can think of it as being below the unstable manifold, excuse me, the unstable poles, and going to adaptation if you're above. In order to do this, we'll think of the system as in terms of U, gamma, and R, because that allows us the right number of dimensions for the ODE system to have projective boundary conditions at t equals the equivalent of -infinity, to have that projection onto the unstable manifold to be 0, to have the projection onto the stable manifold at what corresponds to t equals +infinity to be 0, so that you can solve the system. This is done using BVP 5C in MATLAB, which is a collocation method. It uses polynomials over subintervals with conditions that require a certain amount of regularity at boundaries of these subintervals. It requires an initial guess to the solution as well as boundary conditions. So we take this system and we solve it with a pseudospectral method as a boundary value problem to get the background solution U hat, gamma hat, R hat. And then we use a shooting algorithm, like OD15S in MATLAB, to solve for the solution forward in time from the equivalent of t equals negative infinity to the equivalent of t equals positive infinity. Then again, we take the inner product of that solution to the linearized problem at t equals positive infinity with the unstable eigenvector and show that that inner product is negative. So in summary, just to summarize some of the results. There are some results that have to do with different limits. So for a fixed rate, it can be shown that extinction occurs if the habitat moves too far. So if d, the distance of the habitat moving, is too large, then you expect extinction for a fixed r. And if no extinction occurs in the limit that r goes to 0. That's what this picture on the right was showing as observed numerically and is shown analytically. And then finally, to summarize the main result, we have adaptation for r sufficiently small, extinction for r sufficiently large, and then a tipping point at a critical r value characterized by a heteroclinic connection between the stable pulse at t equals negative infinity and the stable pulse at t equals positive infinity. Some interesting directions for further study would be looking at interactions when there are multiple species, also taking into account stochastic effects, looking at tipping from noise-induced tipping, looking at the interplay between noise-induced tipping and rate-induced tipping, considering the problem in higher dimensions, whereby other more there could be other kinds of interactions occurring and other kinds of interesting characterizations that could be observed. And then to consider periodic forcing corresponding to real life situations in modeling species and habitat interplay. And then finally, to look at early warning signals in actual ecological systems and seeing how the intuition gained from this model could affect the understanding of observing early warning signals and characterizing early warning signals in the actual ecological system. And that completes my talk. Thank you very much.
Great. Thank you very much, Blake.
Thanks,
Appreciate
guys.
it. Thanks for an interesting talk. Yeah, if anybody has any questions for Blake, please feel free to jump in. And I guess, Blake, you can, if your students have questions, I can't see them, so.
Yeah.
I have a question, unless anybody else has one.
Uh-huh.
Oh, I guess Jan Sieber has a question, so I'll let Jan Sieber go first.
Can you hear me?
Yes.
Good. Yeah, so I was interested in when you compute this is a numerical question. When you computed these, you had to compute the unstable, what was this? The unstable direction of there were various, you needed to know the dimension of these unstable subspaces, right? of the t plus and t minus infinity states, right?
Uh-huh.
I'm wondering, does this dimension depend on, like, when you have your rate, you had this tan h there, which is a bit artificial, right? This like the tan, where you had the gamma for the differential equation for the gamma.
Uh-huh. So the
Yeah, so this like does it depend on which choice you make for the differential equation for the gamma? Because you could choose probably many other differential equations. It could decay a little bit slower. That's what I mean, you know?
yeah,
At the boundary.
that's a good point. So this is for gamma of t equals a times tang of RT. It's for that is correct for a very specific one. And we're using it in this larger system because it's useful for looking at the boundary conditions. And I guess you're asking, it sounds like you're asking,
Like, what's the dimension? How did you compute these like the dimensions of these
yeah,
unstable dimensions? Well, that's what you need. The unstable dimensions and the subspaces, right?
right. So first we do the discretization. So we use the statistical method. And then for that ODE system, the dimensions. Now, the gamma replaces the explicit dependence on the t variable for the right-hand side of the PDE. And so adding that corresponds to like you could even just start with a zeroth order approximation of the using the stable pulse, but for some positive time and then let it evolve. And you could evolve it that way. So this corresponds to that effect. So the unstable manifold corresponds to your solution moving forward in time because of the explicit time dependence.
So you implemented proper projection boundary conditions, yeah?
Yeah, we do it in order to get the
No.
numerically the reason we do it to get the projected boundary conditions we want, but it's also a nice way to think about it in terms of the analysis.
Thanks.
I just interject there in response to Jan. It's in this formulation, it's not quite true that the gamma is artificial, actually, because the gamma is actually the ramp function. You don't have to take gamma to be the ramp function, but in this formulation, it was taken to be the ramp function. Do you see what I mean, Jan?
Yeah. Thanks.
Okay, any other questions?
Yeah. So my question was, unless anybody else has questions, was related to the habitat function. You have this kind of smooth, kind of pulse looking like habitat. How different would it be if instead of having a smooth habitat, you had like this piecewise, where inside you had, for example, 1 and outside you had 0? How easy would it be to compute this unstable pulse, being your habitat function is discontinuous? How would you input those boundary conditions in that phase condition to compute, for example, the unstable pulse at positive infinity?
Let's see, that's interesting. So the question is, how would we compute the solution to the time asymptotic system? Okay, let's see. If the habitat function
It's
was
truly piecewise.
piecewise, continuous, like if it was piecewise instead of smooth.
Correct.
Let's see here. That's an interesting question. Let me look at the equation here. I think because of all the pictures, it's a little slow. I'm trying to find the... Okay. Well, okay, so for the pulses, they correspond to t going to plus minus infinity. So there is no h function there. So the pulses would be the same. And then the question is, I guess, how would it affect your solution?
Well, I mean, so
The
just
PD.
we have to be careful because remember when we're computing the pulses, the inner habitat, right? So if you go back to your system, I mean, before that.
Sorry, you want
So I'm talking about the equation where you had the habitat, the the F function where you had explicitly the habitat there.
This here. Uh-huh.
So in my case, when I would modify this, where I would have two governing like Fs, one for the inner and one for the outer. Where for
Uh-huh.
the inner, you would have like one, for example, or H star, and the outer would be explicitly zero. So you have two dynamics governing those.
Mm-hmm.
So then would that be the same to compute the unstable pole? Would you still use, I mean, so you'd have to explicitly use that in your
Yeah.
computations.
My understanding is that you would still be considering, for the unstable and stable poles, you'd be considering gamma of plus or minus infinity, which should correspond to you being on the part of H where it's 0. And so you would have a system that doesn't depend on H really there. Like that part would be 0. So it'd be the exact same system to solve. It'd be the exact same stable and unstable poles, I believe. But that's a great question. I'd love to think about that some more. Yeah, thank you for the question.
Okay.
Any other questions for Blake? Jan, please go ahead.
If I can ask one more. So if instead of a ramp, you just have constant speed moving habitat, then the computation should be much easier. What do you get then? What's the limiting rate then?
Okay, so let me make sure I understand the question. So let's say that gamma of t is equal to like some constant times t.
Yeah.
So you just have it moving at a constant rate.
So you can eliminate and probably like, or no, you should just get it traveling. So I would imagine there should be a traveling, like if the pulse travels at the same, your habitat travels at the same speed as the pulse naturally would travel or something, then that's the limiting.
Let's see, that's interesting because then your habitat is moving over the entire range. Like there's not a,
Yeah.
It's not a finite transition of location.
So that should be, but that should be in a sense, so that you still can ask the question, right? Is the species able to keep up with that constant speed of your habitat, right?
Right. Yes, you could still
And
ask.
I think the answer would be, I don't know if you have a, I don't know how does this work when you have a, so that looks to me like an easier question. That is probably that answer might feed into the more complicated problem that you have studied. I would imagine, right?
Mm-hmm.
If the
So that's been addressed, right? By
exactly.
Vichorik and Chris Hassan.
So it might be a constant that might be one of the asymptotes in your bifurcation diagram, right? You had two asymptotes in the bifurcation diagram there. I don't know, like the D star there. What was it? I don't know. No, this was no. Okay. So just for context, I mean, just to understand, like a simpler subproblem. Okay, thanks.
Mm-hmm. Yeah.
Like our.
Okay. Any other questions for Blake?
Okay, last question, I promise.
Sounds good.
All right, so then in your non-autonomous PDE, you had a specific notation on this y-axis here. Can you talk about that?
Sorry.
I mean, yeah, right here. I mean,
Oh, right here.
yeah.
Oh, okay. I apologize. The caption. So this is work in progress, and the caption does not correspond to the notation used in the talk. So I'm thinking of gamma as a function of t. Gamma equals a tang of RT, but I did not notice that that was inconsistent. Thank you for bringing that to my attention. Is there something more specific you were asking about?
Well, I'm just saying, like, if you look at it, so your U0 here would be representing what? Is it your initial standing pulse? And then T0, and then you have this Z here. So I was just trying to, yeah.
Oh, okay, I see. So the coordinate change is such that Z equals 0 corresponds to the center of the pulse. As so we originally had this pulse that was moving. Sorry, so pulse being the habitat function. We have this habitat function that is moving. And then under the new coordinate change, that habitat function is fixed at z equals 0. And you can, under that coordinate change, then think of the species as moving. So in this figure, we see it looks like the species moves to the right and then comes back to center. And that's because of the coordinate change.
Okay, I see Emmanuel nodding to that. So, okay. Any other questions for Blake? Okay, great. Thank you very much, Blake, for a great talk. And we will have a colloquium next week. I'm sorry for the incorrect subject line saying Blake's talk was the 10th. So I'm glad you all were still able to make it on the 3rd. So much appreciated. And let's thank Blake one more time and see you hopefully next week.
Thank you.